So for a linear polar covalent compound such as HCl, it's easy for us to denote if this thing is polar or not. We know that the chlorine is delta minus, the hydrogen is delta plus, and we can draw a dipole that way. For more complicated molecules, though, we need to get into the shape of the molecule in order to determine whether it's polar or not. So if we start off with a situation with a compound between hydrogen and carbon, we draw the carbon with its 4 valence electrons. So this is a Lewis dot diagram that we're drawing here. We continue to fill it in until the octet is fulfilled. And so we have a carbon surrounded by 4 hydrogens. This is methane. And it takes on a 3D shape. So they're not in the plane of the page here as you might think. They're trying to get away from each other. So these hydrogens and even these hydrogens here, everything's trying to get away from each other as best as they can. And we'll redraw it as we can. So starting with the carbon as the center atom, we're going to draw a line straight up, and this is in the plane of the page. So one hydrogen is straight up in the plane of the page. We're going to have another one in the plane of the page as well. I'm going to draw a triangle here, but really what I want you to imagine is this is a line coming out of the page, and this is a perspective of it. So this is the front end of the line up here, this is the back end of the line, and the hydrogen here is coming out of the page. And to show the hydrogen going away, I'm going to draw a dashed line that actually indicates that this is going away. And so the hydrogen is here. And this now represents a better spatial orientation of the hydrogen atoms. They're all equally away from each other, equal distance away from each other completely. And the bond angle there is 109.5 degrees for each one of these. So it's perfectly aligned, everything is away from each other. Overall, we're going to call this a tetrahedral molecule. The reason why you call it tetrahedral, and I'll try to do this, is if you were to fill in each one of these sides, we would have 1, 2, 3, and then the one on the back side, there's 4, so it's a tetrahedral, 4 sides overall to this molecule. Now we want to deal with nitrogen and hydrogen and see what happens there. So with nitrogen and hydrogen, 5 valence electrons around nitrogen. We're going to use the hydrogens to do a Lewis dot diagram and fill them in. We're going to get the bonds formed with the nitrogen, and note that we have a lone pair of electrons up here as well. Now this does look similar to the carbon with hydrogen molecule, except that up top here we have a lone pair of electrons, and we need to be aware of that. These lone pair of electrons actually push the other atoms further away, because spatially the lone pair of electrons actually are bigger overall than just a hydrogen atom itself. So to redraw the nitrogen then, I'm going to say that my lone pair of electrons are in the plane of the page. This, I am going to draw one hydrogen that is also in the plane of the page. I'm going to draw one hydrogen which is coming away from the page. And I'm going to draw one hydrogen which is going away from the plane of the page. And that's the 3D shape of it. This makes the shape of a period from the nitrogen, of a pyramid, from the nitrogen to the hydrogen to the hydrogen to this hydrogen. That shape overall is a pyramid. So we say that this is pyramidal or pyramidal shape. And we'll move on to one more molecule of importance, and we'll use oxygen and hydrogen as our example. So if I take oxygen, I've got 6 valence electrons around it. I have to use 2 hydrogens in order to make a stable compound, and out of the stable compound I form the covalent bonds, and notice that I now have 2 lone pairs of electrons on the water molecule, or H2O. So I'm going to redraw this as well. Starting from the oxygen, In the plane of the page, I'm going to have one of my lone pairs of electrons. In the other plane of the page, I'm going to have my other lone pair of electrons. Starting to look a little bit like Mickey Mouse. One of my hydrogens I'm going to have coming out of the page. And one of my hydrogens I'm going to have going away in the page. So overall, the shape from atom to atom to atom, this is called a bent shape. Now notice they're all very much related to each other. They're very, very similar. So we compare the three molecules, and we see they're very similar in shape. They all typically start off from the tetrahedral main shape. But as the lone pairs start to become involved, we change the name of it even though the shape is related to each other. This is a pyramidal, and this one we call a bent shape. And then the very last shape for us to understand, of course, is something like hydrogen chloride. So when the two of these are together, this is a linear shape. It also becomes important if we're going to deal with something like carbon dioxide. Carbon dioxide is also a linear shape as well. So now that we know the shapes, or can guess the shapes out of the molecules, we're going to go back to adding in polarity and polar covalent bonds. So we're going to start with the methane molecule first, the CH4. And if we look at the periodic table, the carbon is more electronegative than the hydrogen, so there's a very slight dipole, but the dipole is headed towards the carbon. And the one from this hydrogen is headed towards the carbon, this one is headed towards the carbon, and this one is headed towards the carbon. So all the dipoles are facing in. And overall, these dipoles cancel each other out. So overall, this molecule would be considered non-polar. Now, why non-polar? Let's remember, if it was HCl, the chlorine is a delta minus charge, the hydrogen is a delta plus. There is overall a dipole, but there's nothing canceling out this dipole. It remains. So overall, this is a polar covalent molecule. This one, the methane, these dipoles are canceling each other out. So the dipoles, when they all cancel each other out, the molecule itself is nonpolar. Okay, and now there are cases where the bond can be polar, but still overall the molecule is nonpolar. And let's take a look at another example of that. So we'll do a compound between carbon and chlorine. So we take chlorine, 7 valence electrons, and as it turns out, we go through a similar situation that we do with hydrogen. So if you were to go and do this, finish it yourself, the Lewis dot diagram would look like this, and we'd also end up with a tetrahedral molecule, and instead of hydrogens, we've got chlorines all around. The chlorines are much more electronegative, so they're going to hog the electrons, and the dipoles are going to go this way instead. The hydrogen was there, the dipole went towards the more electronegative carbon. In this case, the chlorine's more electronegative. But again, these dipoles are canceling each other out. So even though this bond overall is polar, so there is a polar bond, all of those polar bonds are canceling each other out. And so overall, this molecule is a non-polar molecule. And so be careful with that. We may ask questions where in the multiple choice answer, we're going to ask for both of these. Is this compound a non-polar molecule with polar covalent bonds? Is it a non-polar molecule with non-polar bonds? And you must be able to differentiate between them. So let's move on to ammonia again. Ammonia had the shape of pyramid, and the lone pair of electrons sitting up top. Now again, nitrogen is more electronegative, so the vectors essentially for the dipoles all come towards each other. Now, if you remember from physics, and by this point in time in the course you guys have dealt with physics, if I look at this arrow right here and I break it down, I can break it down into two components. I can break it down into this component and this component. So both of these arrows make up the green one. So both of these black ones make up the green one. On this hydrogen as well, I've got components that are essentially, let's try to see if we can do this. The arrow's like this, and so I've got components of another dipole that's going straight up and another one that's going towards towards the back side. And then on this bottom one, sorry, this one over here, we got another component as well, where this would be, and we would get another vector here and another vector like this. So as it turns out though, all of these vectors on the bottom cancel each other out. All of these ones get canceled out, and all of these remain. So that is the more scientific way of explaining it. All of these vectors remain. So overall there's a dipole, but it's easier if you just look at the molecule and just say, you know what, all of the vectors overall seem to be adding up, and it looks like the dipole is just going right through this nitrogen. And so overall the molecule would have a dipole. It would run through the nitrogen. The positive end would be down where all of the hydrogens are, and the negative end would end up going up through where the nitrogen is and through the lone pair of electrons. And we'll try this last one with water. So water, we have a lone pair of electrons here, lone pair of electrons here, and we're going to have the hydrogen this way, and we're going to have a hydrogen this way. So same thing, the vectors, oxygen is more electronegative, so the dipoles are going to head this way. So overall, there is a dipole that runs right through the center of oxygen, with the hydrogens being overall delta positive, the oxygen end going to be delta negative, and so the dipole runs right through the middle of the molecule overall. So we would consider this to be a polar covalent compound as well. It also has polar covalent bonds. And I forgot to mention that on the ammonia molecule. Because the dipole is running through it, this is a polar covalent compound. And then, of course, if the dipoles cancel each other out, then the molecule overall is called a nonpolar molecule.